Hello class, this is Ms. Riggins with today's video on section 3.2, the exponential function and derivatives. As you're watching the video, please remember to write down any important vocabulary, formulas, equations, or theorems. Feel free to pause or rewind or even replay the video as often as you need so you can truly understand. And at the end of the video, write down your summary and submit your online summary as well as your top question before class. All right, let's begin. Last video we were talking about the derivatives and power and polynomial functions, but now we're going to look at determining the derivative if the function is an exponential function. So if you recall, exponential functions look like a to the x, where a is some constant and we like a to be greater than 1. And the graph of it looks like as such. So the question is, what do you think the derivative of this function will be? Well, remember the derivative is the slope of the tangent lines at each of the points. So if I were to draw different tangent lines, you know I can't draw straight lines, but it seems like all the tangent lines have increasing slope. And so that means that the derivative function is going to be a positive function for all x, since the slopes of the tangent lines are all positive. And it seems like the slopes of the tangent lines are increasing as we move further along the x-axis. Well, that looks very similar to the actual exponential function and the properties of the exponential functions as well. So since the derivative is positive for all x values and the rate of change, well, the slope of the tangent lines are increasing, which means that the graph is concave up as well, it seems like the derivative function will be very similar to the original exponential function. So what we should do is let's take a look at the formal proof. So if f of x is equal to a to the x, the derivative of f at x will be the limit as h approaches 0 of this difference quotient. In this case, f of x plus h is a to the x plus h, and f of x is a to the x. Sorry. And when I do some law of exponent properties, I end up being able to factor out an a to the x of the equation. And the reason why of the limit. The reason why I can factor out an a to the x is because of the fact that h is changing for the limit, not x. A to the x is actually a constant value if we're trying to find the derivative of f at x. So really, in order to determine our derivative function, we know that it's going to involve a to the x, but it's also going to involve multiplying a to the x times the limit of some function of this function a to the h minus 1 over h. So let that be equal to, let's call it a k value, okay? I'm going up here so we can see that. So far what we can say is that the derivative of f, the exponential function, is going to be the result of multiplying a to the x times some k value, where k is the limit as h approaches 0 of a to the h minus 1 over h. So let's take a look at what this limit is numerically. So what I did is I set various h values from negative 0.1 to closer to 0, and then I'm from the other side from 0.00001 all the way to 0.1. And I looked at this difference value quotient for different values of a here being 2, a here being 3, and a here being 4 and 5. And it seems like as I take the limit of these values as h approaches 0, we seem to get that for a, it's around, for a equals 2, that limit k is about 0.693. And for 3, it's about 1.09861. For when a is 4, it's about 1.38. And when a is 5, it's about 1.60942. And that is, and we can verify it because it's on both sides as h gets closer to 0 from the positive and the negative side. So we look at this k value, which is that limit, and I made the table to kind of summarize the results. We see that as a increases, that this k value also increases as well, but the k value is always positive. So now I have a way of determining what the derivative of a to the x is. It's a multiple of a to the x, and that multiple is varies based off whatever a is. But here's a question. If the derivative of a to the x is the result of being a multiple of itself, what happens if k is equal to 1? So the question is, what a value would it need to be so that my k value, that limit that we talked about of a to the h minus 1 over h, would be equal to 1? Well, since the k seem to be increasing as a increases, then it seems like whatever this a value is, it's going to be somewhere in between 2 and 3 because of the k values for 2 and the k values for 3. So let's come up with a way to determine what that answer would be. So what is a so that that k value is equal to 1? So we set that limit equal to 1. And really what we want to know is for really small h, because as h gets closer to 0, what does a need to be such that a to the h minus 1 over h is really close to 1? Okay, so doing some algebraic manipulation, if that's we want that to be close to 1, then a to the h minus 1 should be close to h, and therefore a to the h must be close to 1 plus h. And so a, or take the root of both sides, h root, we want a to be close to the number 1 plus h to the 1 over h. Okay, so this is nothing but algebra right here. Let's take a look and see what that is when h gets really close to 0. So here we have our h being really close to 0, going from a bigger negative number to a small negative number. To 0, and then going from very small positive 0 to large. And as you can see, it seems like the values for that quotient seem to be, that 1 plus h to the 1 over h, seem to be getting really close to 2.718 something. And where is that number familiar? Where have we seen a number close to that? Well, if you said e, you'd be absolutely correct. As h approaches 0, 1 plus h to the 1h is really close to 2.718. So it seems like the a that makes that true, it should be a that should be equal to 2.718, or e. So therefore, the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. Now, why is that a big deal? Well, remember, we said that we're trying to find that k is equal to 1. So if k is equal to 1, when a is equal to e, then that means that the derivative of a to the x, i.e. e to the x, is going to be equal to 1 times itself. So in other words, for e, the derivative of e to the x is exactly itself. If a is not e, then that means the derivative of a to the x is equal to a multiple of a to the x. Whereas if a is e, the derivative of e to the x is only exactly itself, e to the x. So the next question may ask, well, if a isn't e, how do we determine what that k is? How do we determine what that limit is? Do we have time to numerically go into a table of values and get h really small to see what the value is close to? We can do that, but there's a way we can determine this analytically, and I wanted to show you that way. Okay, so remember that we're trying to figure out what k is in this situation. So let's do something a little bit different. Let's replace a with e to the natural log of a, which is essentially the same thing. We haven't changed any value. A is the same thing as e to the natural log of a because of the inverse properties of e and natural log. So then doing some simplifying and rearranging, we get that this is also equal to e to the L and a over h. To the h. Well, yeah, you guys see what I'm talking about. Moving on, let's do some substitution here. let some variable t be equal to h natural log of a. So that's basically just rearranging this. So let t be equal to that. And therefore my h now will be equal to t divided by natural log of a based off this relationship. So I'm going to rewrite this part based off now t. And we get e to the t minus 1 over t over natural log of a. Doing some algebraic simplification and manipulation, this becomes natural log of a, which we can pull out because it's not dependent on t. So we pull that out. And we just are left with e to the t minus 1 over t times the natural log of a. And as we can see, for what you may recall, the limit of this is going to be 1. And since the limit of this is 1, then that means that to determine what k is, all that is it's the natural log of a times 1, or the natural log of a. So instead of saying some variable k, some constant k times a to the x is the derivative of a to the x, now we have a more specific way of determining what that is, as it being just the natural log of a times a to the x, which makes sense because if you remember, when a is e, the natural log of e is equal to 1. So no wonder why this works when e is equal to a is equal to e. So I know that was a lot of proving theorems, so I encourage you to go back and take a look at it to truly understand it. But now we've added another derivative formula to use when we're trying to find the derivative of things. We talked about last time with power functions and polynomials, and now we've added exponential functions, whether they be a is e or a is any number greater than 1. All right, that's it.